Okay, in this video, we're going to take a very simple transformation and we are going to look at what kind of frequency behavior does that transformation show. And the transformation that I want to deal with is basically yn. So let me write this here. So yn equal to 1 over 2 xn plus xn minus 1. Okay, so basically I'm taking two values and I'm taking the average of the two values, and the output would be the average of these two values. Okay, so think of a system like this. So here's a system. So this is my digital signal processing system. So I'm going to write it as a DSP and the input is X. Okay, and the way this, and the output of course is Y. And the way this DSP works is that you take it's got a memory, so it's got, let's say, 1 bit of memory, or let's make it easy and make it 2 bits of memory. So you get an x into it, so you have xn here and you have xn minus 1 here. So n is the, actually it's going to be the opposite, wouldn't it? Because x is coming from this side, so the present value is going to be stored here in n, and the past value is going to be stored at in n minus 1. Okay, and then what you do is you take these two values, you add them, and then you divide it by half, and that you store it on another location, and that becomes your y, or the y goes out of this place. This is memory location n. So for every time you take the value that is coming at that instant and the value and the previous input that had come in the previous time instant, average them, and that is your output. Okay, so so that's our system, and we want to analyze this system and we want to see how um, what kind of frequency domain characteristics the system has. So we can get the frequency domain characteristic by looking at this equation, right? And we can write the z transform of this equation. And if we write the z transform, what would we get? We would get yz equal to 1 over 2 xz plus z to the power minus 1 xz. And which means that we can write the transfer function, or the z transform of the system itself, as yz over xz, and that is going to be 1 over 2 1 minus z inverse. Is that all right? Okay, so now what do? We want to find out the frequency response of this of this system. So what we want to find out is basically h e to the power j omega, and we can do that by substituting z equal to e to the power j omega. So we get 1 over 2 1 minus e to the power minus j omega. Now let's kind of simplify this so that we can actually plot it. So what we want to be able to do is we want to be able to draw a graph like this, where you have omega on the x-axis and h on the y-axis, right? So to be able to plot this, let's just do that. Actually, on the y-axis you want mod h, and that would kind of give you the magnitude response. So what is this going to be? You can write it as e to the power minus j omega over 2 over 2, and then the thing inside the bracket becomes plus j omega over 2 minus e to the, oh, actually this should not have been a minus, it's a plus, and therefore this is a plus and this is a plus. So e to the power minus j omega over 2. Okay, and this can be written as e to the power minus j omega over 2 times 2 cos omega over 2. and therefore this is e to the power minus j omega over 2 times cos omega over 2. So that's our frequency response, right? So that's the frequency response, and we want to use that to plot and see what the shape of the frequency response looks like. So let's do that in the next slide. So here what we have is, so what we calculated was h e to the power j omega equal to e to the power j omega by 2 times cos omega over 2. Now if you take the modulus of h e to the power j omega, you know that this term is basically a sinusoidal signal, right? It's e to the power j omega 2, its magnitude is 1, so we can ignore that. And what we get is mod of cos omega by 2. So let's now try to plot this, and hopefully that would give you an idea of what the frequency response looks like. So let's take this graph here. So that's omega, and let's plot it from 0 to 2 pi. Remember, we know that in the digital domain, the frequency response, the only unique part of the frequency response is from 0 to 2 pi. If you are able to plot that, then we have all the rest of the frequency spectrum automatically. So let's do that. So this is mod h. Okay, so what would be the value of mod h when omega equal to 0? So you can take a look. Omega equal to 0, which means omega by 2 is 0. So we have cos 0. What is the value of cos 0? 0, right? So it's cos 0 is 1. So 1. Now when does cos omega by 2 become 0? Cos omega by 2 will become 0 when omega is pi, right? Cos pi by 2 is 0. So when omega becomes pi, then this becomes cos pi by 2, which becomes 0. So at a frequency of pi, this is the value. Now you know the shape that cos takes from 1 to 0. So the shape is going to be approximately like this. And what will be the value at 2 pi? At 2 pi, this becomes omega equal to 2 pi. So this becomes cos pi. Cos pi is minus 1, but we are taking the modulus here, so it will be 1 again. So again, the value is going to become 1. So it's going to go like this. And this is going to be repeated on both sides. So we can plot it by repeating the same pattern on both ends, right? So cos, and then this goes. So it just keeps repeating itself on both sides like this. So that is our characteristic. Okay. Okay, let's stop here in this video, and then in the next video what we'll do is we'll discuss whether this is, what kind of characteristic is it? Is it a low pass characteristic? Is it a high pass characteristic? And what can we say about that?